A magnitude 7.7 earthquake just struck the exact same region of Japan that was devastated by the 2011 Tōhoku disaster. They are describing it as a loading event, the same coastline that watched a wall of water arrive 14 years ago, that was already carrying more unrelieved strain than at any point since 2011. Tsunami warnings were issued immediately. Evacuation orders went out across multiple prefectures. Japan's early warning system, the most sophisticated on Earth, pushed alerts to every mobile phone in the affected region within seconds of the first seismic wave being detected. The machinery of the most earthquake-prepared nation on the planet activated instantly and completely. Nuclear facilities went to emergency protocols. And yet the scientists monitoring this system are not relieved. They are not describing this as a stress release event that lowers the risk going forward. They are describing it as a loading event, a rupture that has redistributed stress across a plate boundary system that was already carrying more unrelieved strain than at any point since 2011. Because here is what the seismic community knows that the news coverage isn't telling you. A magnitude 7.7 on the plate boundary that produced a magnitude 9.1 in 2011 is not a significant stress release. On the energy scale that governs megathrust ruptures, a magnitude 7.7 releases roughly 1% of the energy of a magnitude 9.1. A magnitude 7.7 releases roughly 1% of the energy of a magnitude 9.1. It does not reset the clock. It does not relieve the accumulated strain. In some configurations, it loads adjacent segments further. Japan is not breathing easier after this earthquake. Let's get into it. The location of this earthquake is not incidental. It is the entire story. And to understand why, you need to understand what happened to the stress field of Japan's subduction system after 2011, and what has been happening to it every day since. The 2011 Tōhoku earthquake ruptured approximately 500 kilometers of the plate boundary, where the Pacific plate subducts beneath the North American plate along Japan's eastern margin. It was a rupture of extraordinary scale. The fault surface that slipped measured roughly 500 kilometers long and 200 kilometers wide. The maximum slip at the center of the rupture exceeded 50 meters. 50 meters of plate boundary movement in a matter of minutes, releasing accumulated strain from centuries of plate convergence simultaneously. Sections to the north, toward Hokkaido, and sections to the south, toward the Boso Peninsula, and the transition zone where the Pacific plate boundary meets the Philippine Sea plate boundary, did not rupture in 2011. Graphics showing arrows of energy pushing from the 2011 zone into the northern and southern zones. They were pushed closer to their own failure thresholds, and they have been accumulating stress ever since. The current M7.7 occurred on the southern portion of this system, in the transition zone where the stress transferred from 2011 intersects with the stress loading from the northward pushing Philippine Sea plate. This is not an area that seismologists consider low risk. It is an area that seismologists have specifically flagged in published research following 2011 as having received positive Coulomb stress loading from the main rupture and as being in an elevated probability state for subsequent large events. The earthquake happened exactly where the models said to watch. That is not reassuring. That is the models being correct. And the models also say that a M7.7 in this location does not resolve the stress accumulation in the system. It reshuffles it. The segments that were critically loaded before this earthquake are now loaded in a slightly different configuration. Some may have been partially relieved, others may have been pushed further toward failure. The Coulomb stress calculations are being run right now, and the preliminary picture they are producing is the reason Japan is not standing down. I want to spend time on the physics here because it is fundamental to understanding why this earthquake, significant as it is, does not represent a meaningful release of the stress that makes Japan's tectonic situation so dangerous. The magnitude scale is logarithmic. Each whole number step represents approximately 31.6 times more energy released. The difference between a magnitude 7.7 and a magnitude 9.1, the size of the 2011 Tōhoku earthquake, is therefore not 1.4 times more energy. It is 31.6 multiplied by 31.6 raised to the power of 1.4. The 2011 earthquake released approximately 180 times more energy than today's M7.7. Put another way, it would take roughly 180 earthquakes of today's magnitude, all occurring on the same fault segment, to release the equivalent energy of the 2011 rupture. And the plate boundary that produced 2011 has been recharging at the same convergence rate of 8 to 9 centimeters per year every year since. In the 14 years since 2011, the Pacific plate has converged approximately 112 to 126 centimeters, over a meter of accumulated elastic strain on the sections of the boundary that did not rupture in the main event. That strain is stored in the locked fault. It does not dissipate. It does not leak away gradually through microseismicity. It accumulates until the fault slips. Today's M7.7, releasing 1% of the energy of a 9.1, has not made a meaningful dent in that accumulated strain budget. The fault segments that carry the majority of the post-2011 stress deficit are still locked, still loading. and now carrying the additional stress transfer from today's rupture on top of the 14 years of post-2011 accumulation. This is the mathematics that Japanese seismologists are working with right now. And it is why the official response to this earthquake is not relief, it is heightened vigilance. The aftershock sequence following a major earthquake is not just noise, it is data. And the aftershock sequence from this M7.7 is producing data that seismologists are reading very carefully. Standard aftershock sequences follow a predictable decay pattern described by the Omori-Utsu law. The rate of aftershocks decreases as a power function of the time elapsed since the main shock. Deviations from this expected decay pattern are informative. A sequence decaying faster than expected suggests the fault system is settling rapidly into a new equilibrium. A sequence decaying slower than expected, or showing bursts of elevated activity beyond the expected decay, suggests ongoing stress redistribution, fluid movement in the fault zone, or the possibility of additional significant ruptures. The current sequence from the M7.7 is showing characteristics that seismologists describe as requiring continued monitoring. The spatial distribution of the aftershocks, the geographic pattern of where they are occurring relative to the main shock rupture, this is called an aftershock migration pattern. Additionally, the depth distribution of the aftershocks includes events at depths below the main rupture zone. Deep slab seismicity following an interface earthquake can indicate that the main shock has loaded the slab mechanically, in ways that may produce additional surface felt events as the slab adjusts. None of this is conclusive. Aftershock sequences are inherently difficult to interpret in real time. Cinematic macro shot of deep earth rock layers shifting slowly. Abstract visualization of waves of energy propagating outward through deep rock structures. Wide shot of a tall coastal tsunami siren tower silhouetted against a dark, stormy sky. That response, the speed of the warning, the scale of the evacuation orders, the activation of the full emergency machinery, reflects 14 years of investment in improving the response systems that were overwhelmed in 2011. The waves that arrived at the monitored tide gauges were smaller than the worst-case projections for an event of this magnitude. 3D model of the earthquake rupture showing it pointing away from the surface. Animation of the seafloor pushing up rapidly and displacing a massive volume of water to create a tsunami. Side view showing the earthquake focused deep underground, which is why the waves, while real and recorded, did not reach the catastrophic heights that a shallower, higher slip event of similar magnitude would have produced. But here is what the tsunami response tells us that goes beyond the immediate event. The 2011 tsunami response revealed in brutal detail the gap between designed evacuation infrastructure and actual human behavior under extreme stress. People drove toward the coast to check on family members. Others delayed evacuation to secure property. The roads were congested with people moving in the wrong direction. Seawalls that communities had trusted provided false confidence that delayed evacuation decisions in some locations. The post-2011 evacuation culture in the affected prefectures has changed significantly. The communities that experienced 2011 firsthand have internalized the imperative of immediate vertical evacuation at the first sign of shaking. Compliance with today's evacuation orders in those communities was high and rapid. But the Nankai Trough scenario, the event that Japan's planners describe as the national catastrophe event, would affect the southern Pacific coast. Communities that did not experience 2011. Communities where the tsunami culture, while improved post-2011, has not been tested by a real event. Communities where some of the same behavioral patterns that cost lives in 2011 may still be present. Communities where the tsunami culture, while improved post-2011, has not been tested by a real event. The systems performed, but the test was not the worst case. But here is what the tsunami response tells us that goes beyond the immediate event. Before this earthquake, Japan's official assessment placed the probability of a major Nankai Trough rupture at 70 to 80% within 30 years. That number, already extraordinary for any single hazard event in a developed nation, was based on the historical recurrence record and the current stress accumulation state of the fault prior to today's event. That assessment is now being updated. The mechanism by which a M7.7 on Japan's eastern subduction zone affects the Nankai Trough probability is complex but real. That response, the speed of the warning, the scale of the evacuation orders, is mechanically connected to the Pacific Plate through the crustal stress field of the Japanese archipelago. Stress events on the Pacific Plate boundary propagate through that crustal stress field to the Philippine Sea Plate boundary. The magnitude of the effect and its spatial distribution depend on the specific rupture geometry and the elastic properties of the intervening crust. In August 2024, following a significant earthquake near the Nankai Trough's eastern end, the Japan Meteorological Agency issued its first ever Nankai Trough Earthquake Extra Information Notice, a formal government communication acknowledging that the rupture probability had increased above its already elevated baseline. That notice was lifted after 2 weeks without a major event. The framework that notice represented, formal government acknowledgement, that one earthquake can and does elevate the probability of a Nankai rupture, is now active again. The seismological community is running the same calculations it ran in August 2024, updated with the new rupture parameters from today's M7.7. Japan's Cabinet Office Nankai Trough scenario projects 323,000 fatalities in the maximum considered event. The complete disruption of the Tokai Industrial Corridor, the manufacturing backbone of the Japanese economy, for months to years, and tsunami waves arriving at some Nankai coast communities in 3 to 5 minutes, faster than the warning system can complete its cycle in some locations. That scenario has not changed. What has changed is its probability in the near term. And near term, in the context of a fault that produces major events every 100 to 200 years, and last ruptured 80 years ago, means now. Japan's response to this earthquake goes beyond the immediate emergency management. At the governmental and scientific level, a set of processes has been activated that reflects the seriousness with which Japan's institutions treat connected seismic risk. The Earthquake Research Committee, Japan's senior scientific body for seismic risk assessment, convenes within days of significant earthquakes to assess the implications for connected fault systems. Their assessment following this event will be published and will directly inform government preparedness posture. The Cabinet Office's Central Disaster Management Council, which oversees national catastrophe planning, including the Nankai scenario, will review the stress modeling outputs as they become available. If the Coulomb stress calculations indicate meaningful loading of Nankai trough fault segments, the Council has protocols for elevating preparedness measures across the affected prefectures. At the prefecture level, emergency management agencies in Shizuoka, Aichi, Mie, Wakayama, Kochi, and Tokushima, the prefectures most directly in the Nankai trough impact zone, are conducting readiness reviews. Tsunami evacuation tower access is being checked. Emergency supply stockpiles are being assessed. Communication systems are being tested. This is not panic. This is a highly functional, institutionally sophisticated response to a genuine probabilistic shift in near-term seismic risk. Japan has built these systems precisely for this situation, the situation where one significant earthquake changes the probability calculus for a connected, larger event. The question is whether the event they are designed to respond to will arrive before the preparations are complete. Here's what I want you to take from this. A M7.7 earthquake striking the exact region of the 2011 Tōhoku disaster is significant in itself. The shaking was severe. The tsunami warnings were real. The evacuation was large-scale. These facts alone warrant your attention. It redistributed stress onto adjacent segments that was already carrying more unrelieved strain than at any point in the post-2011 period. It ruptured a segment that the models flagged as elevated risk, and it has triggered the formal reassessment processes that Japan's scientific and governmental institutions have built, specifically to evaluate whether a larger event has become more probable in the near term. The Nankai trough probability was already at 70 to 80% in 30 years before today. The models are now being updated with today's data. Japan's institutions are responding with the seriousness this situation demands. The energy mathematics are not ambiguous. A M7.7 is not a meaningful stress release on a system that produced a 9.1. The fault is still loaded, the plates are still converging. The clock that governs megathrust recurrence has not been reset. I will be tracking the Coulomb stress model outputs as they are published, the official Earthquake Research Committee assessment when it is released, and any updates to the Nankai trough probability from the Japan Meteorological Agency. Because this earthquake is a data point, and the data it adds to the sequence is not pointing toward a lower risk future. Subscribe and turn on notifications. Japan is bracing for something bigger, and the data says it should be.